2 times 4, don't forget to square the 2 there, that's actually 8x squared, minus x to the 5th, and that's going to be 2 times x squared squared, that's actually 2x to the 4th, and it is after that minus sign, so it's getting subtracted. Okay, so good thing you simplified it, because a pair of these are opposites. So that way, by the time you get to doing your outer iteration of the integral, you're now going to do the 0 to 2 limits for what's left over. The 8x squared minus x to the 5th. And then that turns into 8/3 x cubed minus 1/6 x to the 6th. And this is a polynomial, so this is one where you plug in the 2, you'll get an answer, but the 0 is going to wipe everything out. So 8 times 8 is 64 thirds minus, oh that's nice, 64 sixths. A third minus a sixth is a sixth, so that's technically 64 over 6. And that reduces, my friends, to 32 over 3, I do believe. So that should be the value of this integral, whatever it stands for. What was the first context I mentioned last week on, did I make a mistake? Please point out mistakes. I know you're making me nervous. I made a mistake. What did I do? 1/3 minus 1/6. I did that right. 1/3 minus a 6 is a 6th, so that's right. Okay. I get paranoid. Okay, so please don't hesitate to let me know if I make a mistake. I'm not above reproach. But what was the first context I mentioned tied in with double integrals? Volume, yeah. You don't see the 3D volume here because this is the domain of the integral. The function we integrated right here, for values of x and y in this region, x cubed would be positive, 4y would be positive, except at the origin, they both be 0. So that means there is some surface up above here that plays the top of the solid. And then going straight down from that surface to the xy plane, that will be the 3D object that 32 thirds represents the volume of. So this could be tied in with the volume scenario, okay? With that being its underlying region as opposed to a rectangular base like the ones we did last Thursday. Now let me ask you this. A very essential skill to have is to be able to change the order of integration. This integral right here was originally in dy then dx order. So I'll just generically call it f. dy dx is the original order that we did there for this region R. What if we wanted to switch it to dx dy? One thing that makes double integrals over rectangles really, really, really sweet is changing the order is just changing the limits. No such love here, because your outer integral has to have constant limits. You can't just switch the x squared to 2x to the outside, because now you've put variable limits on the outer integral, which is impossible. So what you have to do is start with your shape, your region R right here. Oops. And keep in mind what its bounds are. Intersects down here at the origin, intersects up here at the point 2, 4. This is the curve y equals 2x, and this is the curve y equals x squared. So what I want to do is I want to commit to changing the order of integration. I want to do dx first, and then dy last. Can y'all see that pretty well? I want to do lower and upper for x and for y to see what the new limits would be. So if you're committed to doing dx first, you want to start with a full-blown two-dimensional version of your shape. And then going in the x direction, which again, index finger, tell me which way that is. Okay, going in the increasing x direction, you want to double check a couple of things. No matter which way I draw that horizontal ray that goes in the increasing x direction, will I always enter on the same equation boundary, and will my exit always be the same equation? No matter where I draw it, if I draw it here, if I draw it here, if I draw it there, am I always entering and exiting on the same boundaries? I'll always enter on the line and I'll always exit on the parabola. If that's the case, then reversing the inner order of integrations okay, you can do it. If you have inconsistent boundaries, like on a region like this, let's say you got a parabola like here, and then a line like that. Because you may have a parabola opening down, and then a line that kind of slices it off at the bottom. If I do the y direction first, do I have consistent boundaries for entrance and exit?
Yes.
Yeah, you'll always enter and exit on the line. You'll enter on the line and exit on the parabola. But if I do the x direction first, do I have consistent? No, I don't, because there's a split right here. Here you would enter on the parabola and have to exit on the other half of the same parabola. But down below that intersection point, you'd enter on the parabola and exit on the line. So if there's ever a break in your boundaries like this, that causes you to have more than one double integral to evaluate that integral for the region. So always go for the most efficient integral you can, the one that's only going to require one order of integration to get it all consistently done. Okay? So here, it's okay either way. Doesn't matter if we do y then x, we did that first on the paper, or we switch to dx and then dy. So what you got to realize is when you're going in the x direction first, you're entering on x equals some value. That left boundary is defined by x equals what? You gotta be careful.
0.
Not 0. 0, x equals 0 is right there.
Y2.
Yes. The first entrance boundary, not bad for tardy man. Yeah. The first entrance boundary is going to be defined as x equals half y. So sometimes you need to take your equation and redefine the way they're solved. So instead of calling this y equals half x, correction, y equals 2x, you want to rewrite it as x equals half y. Is that still going to produce the same graph? Yeah, two different versions of the same equation, but now, because our first direction of integration is x, we need to have the definition of that entrance boundary as x equals something. So that entrance boundary, no matter where you go in at, you're always entering at x equals 1/2 y. And then where are you exiting?
X equals square root of y.
Yeah, you have to redefine that one also, because the first boundary is defined as x being a function of y. You've got to redefine this other boundary as x being a function of y. Now there's a danger there. Whenever you take square roots, you got to consider that plus or minus. What let Nicholas know that he needed the plus?
It's in the positive part.
Or was he looking?
Yeah,
It's only on the positive side where the x is positive. So if you happen to be over here and you need that square root, you actually have x equals negative square root of y for the left half of that same parabola. So x's entrance boundary is always going to be x equals half y. X's exit boundary is always going to be x equals root y. You don't have to write these little x equals up there. You're just saying x goes from 1/2 y and exits at root y for x's limits of integration. Now here's what you do for the y. This is the outer limits, and the outer limits on a double integral are always going to be what kind of values? They're always going to be constants. What I recommend doing is taking the trash compactor from Star Wars. Any Star Wars reference while I've been in math classes, awesome. The trash compactor from episode 4, A New Hope, they're all Han, Leia, Luke, and Chewie. They're in the trash compactor. The walls are closing in like this. Take your graph, smash it to the axis that you have left to do. If this graph is entirely smashed to the y-axis that I have left as my last dimension of the domain of this integral, then what's the lowest y smudge that's going to be on here from the smashing? 0. And then all this stuff, smash, 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 stops at the y value 4. So essentially, you have variables for the first order of integration, but then your outer limits are always going to be constants, and they happen to be the constants that define that variable for this domain. So you just look at it. The lowest value of y is 0, the upper value of y is 4, because you're dealing with the outer limits. They always have to be constants. So it's a different looking, set of integrands that you have there, or set of limits, but if you apply these limits to the same function, you get the same 32/3. You have to, because, well, it's essentially measuring the same thing. If you are a doubting Thomas, just in case, and what was the lower limit for x? It was half y
Yes.
to root y. So see, comparing the original and the new one, it's not as easy whenever you don't have a rectangular domain. You can't simply just, reverse those like you could with a rectangular domain. Here, it's a lot more involved. You got to analyze the graphs, consider the inner exits, the entrance and the exit, and then the two-dimensional aspect of the region R that you're looking at. And so it's kind of hard to see how you go from this to this without the use of that graph. So you're going to need to start doing some graphing, especially with the double integral domains. You'll need to almost, not every problem, some of the problems are just, boom, evaluate that. And then you don't have to graph the underlying region, you just integrate, plug in your limits, and get a constant at the end. But sometimes the problems may require you to reverse the order of integration, or leave it up to you to choose the order of integration. And you want to choose, in some cases, the most efficient. Would this lead to any more difficult integration than this? If I integrate x first versus integrating y first, do you see any potential snags or possibly more complicated integration in the order of doing the reverse order? Yeah.
Square root of y.
The square root's the intimidating thing there. But notice, if I integrate x first, x here is going to be raised to an even power. The x here is going to be to a first power. So if you had all even powers, that root's not going to be a problem. Because, raising a root to an even power is going to get rid of the radical. So that might be one little tiny snag. But just, in terms of power rule, that's just an exponent of 1/2. So I just want to double check and see if I get the same answer. You don't have to do this for every double integral. If the problem is presented like that, integrate it like that, as is. You'll get the same value that you need to get. I just want to prove it to you that it doesn't matter which order in some cases. Some cases the order doesn't matter. Some cases the order is very important. But in this case, I don't think it's going to be too much of a snag, except for maybe the square root. So when I integrate x first, do you mind if I abbreviate that as me about to integrate with respect to x first? Just using an integral symbol with dx, and then going straight to the x antiderivative here. Okay, so then if I plug in y to the 1/2 first, it's going to be 1/4 y to the 1/2 to the 4th, so that'll ultimately become y squared plus 4 y to the 1/2 times y. So that's what I should get when I plug y to the 1/2 in for all the x's. Okay? And again, you got to make sure you're aware of that. I just integrated x. X is my integration variable. X is what these get plugged in for. Upper limit got plugged in, minus your lower limit getting plugged in. So that's going to be 1/2 of y, oops, not square y, but 1/2 of y to the 4th, plus this. So again, before you go to integrate your next variable, take the liberty of simplifying your algebra, bless you. That's going to be 1/4 of y squared plus 4y, you're multiplying there, so add those exponents, 4y to the 3/2, minus 1/4 times a 16th, so that's actually minus 1/64, y to the 4th there. Fractions are your friends, don't worry. 2 goes into 4 twice, so that becomes 2y squared, and you're subtracting that also. So, kind of funny, the first and last one, the first one were like terms, and these are also like terms. So when I go to integrating with respect to y, let me go and take the liberty of doing that. A quarter minus 2, so 8/4. All right. So I've done my inner integration, and that's the one that's always going to be algebraically intense because you're plugging in variables for other variables, and you're leading with a variable expression. When you get to the outer integral, you're always going to be back in calculus 2. It's just a constant limit integral, one variable antiderivative. So now when I do the antiderivative with respect to y, it's going to give me y to the 5/2, 2/5 times 4, usually 8/5, minus y to the 5th, divide that by 5, that's going to be 300 plus 320. I'm getting nervous. This isn't looking like numbers we still lead to our answer, but we'll double check and see. And then 3 times that's 12, y to the 3rd, And my limits here are from plugging the 4 first, and 4 is going to work well with that half exponent, don't freak out. That's going to give you just a square root for 4, so you should get a rational number as the result. And 0 will plug in and annihilate everything. So when I plug in the 4, the square root of 4 is 2, 2 to the 5th is 32, so that becomes 8 times 32 divided by 5, plus, or no, minus 320 in the denominator, 4 to the 5th. Don't ask me how I knew that. And then minus 7/12 times 64, and then 0 wipes out everything in that polynomial, so I'm going to go liberal with my frac button. 8 times 32 fifths minus 1024 over 320 minus 7 times 64 over 12. Math, boom, frac. Dun, dun, dun. 32 thirds. Okay, you can't see from the glare, but I promise it's there. 32 thirds. Okay. Which means I would probably have stuck with the original dy dx order integration. I guess in hindsight, maybe the square root caused a little bit more algebra up there, you know, at the beginning than just the, you know, the 2x and the x squared it had here. But you're always guaranteed, even if you change the order of integration, yeah, that was probably the best way to go. So apparently some of you may develop the mindset of avoiding square roots when possible and avoiding fractions when possible. You don't have to. Sometimes they're unavoidable. But I just want to let you know that if there is a consistency to this seeming madness, you know, you should get the same answer both ways, regardless of the order of integration. And your integration really depends on this shape too. Not necessarily about the potentially messy algebra or messy calculus that you get. Although if you can see, you know, kind of like a chess player, anticipate a few steps ahead to see what your potential integration would lead to. U sub versus integration by parts, I'd probably stick with U sub, you know. But also this kind of dictates your order of integration. If, you know, you choose to do the y direction first, you want to let your paramount guideline be, am I always going to enter on the same boundary? You'll always, in the y direction, you'll always enter at y equals x squared. You'll always exit at y equals 2x. So since you have consistent entrance and exit all the way across in the y direction, dy could be done first, no problem. Same thing in the x direction. If you're going horizontally in the increasing x, your first x entrance is x equals half y. Don't forget you have to redefine the curve whenever you're going laterally in the x direction. You exit at x equals root y. No matter where you draw a horizontal ray, you always have the same entrance, the same exit. And then you flatten into the y-axis, 0 to 4 are your y limits. Just like here, we did y first from parabola to line, and then you flatten into the x-axis, and then 0 to 2 is the smudge that's left for the constant limits on x. And that was, you know, given to us in the problem. Okay. So not too much of a stretch. Let's see how hard I can make it. Isn't that every math teacher's goal?
Yeah.
Okay. Sometimes you will need to define the limits of your double integral. Okay. And in this context, it's still volume. So a lot of the homework problems or some of the example problems are going to be kind of touted as volume problems. If the problem is described as being a volume, you can take for granted that whatever your underlying region R is in the xy plane, whether it's a rectangle or bounded by curves like this, the function will be graphed entirely above it, or maybe have one z-intercept on the region itself. So that means whatever your 2D region R is underlying is the base of the solid, the function is the top of the solid, and you're finding the three-dimensional volume between here on the xy plane and the function up above it. Okay. You don't have to graph that. You don't have to graph the 3D part, but most cases on double integrals, you at least. You okay?
Well,
you at least need to. Pardon?
Got the right answer.
Okay, good deal. You need to at least graph the underlying region. Okay. So I want to determine the volume of the solid region bounded above by the paraboloid. So in other words, this is our integrand. Is that a vocabulary word each of you know? Integrand means it's the function you're integrating. So that's what's going to go inside of our double integral once we get its limits set up. It's bounded below by the region of the xy plane, bounded by, a lot of use of the word bounded here, bounded by the lines y equals x, y equals 1, and x equals 0. Can you see what that shape is without graphing it? I mean, some people are kind of calculator dependent on the graphing, some people can kind of visualize that, and I need to make sure everybody's on the same playing field.
Triangle.
It's going to be a triangle, yeah. Y equals x, if you graph this underlying region, actually, yeah, I really only need to graph this much of the xy plane. Do you see why? Versus actually centering the origin in the middle of my graph. Because I think everything's going to turn out to be in the first quadrant. If you graph y equals x is your 45-degree line, slope of 1, and intercept at the origin. Y equals 1 is a horizontal line looking like this. And then x equals 0 is better known as the y-axis. So when you graph all three of these, curves, even though each one of them is a straight line, they do make a bounded region. I mean, technically, they break all of the 2D region into 1, 2, 3, 4, 5, 6, 7 regions in 2 space. But of all 7 regions that they create, only one of them is a finite, bounded region that you can use as the domain of a double integral. So whenever you're looking at the word bounded, you want to graph all the curves involved that are mentioned in the problem, and you're looking for whatever bounded, region that they actually make. This triangle is the only thing that's bounded. Everything else is unbounded. Because if you go from the line here, y equals 1 upward, you have that as a boundary, this is a boundary, that is a boundary, but you have no upper boundary. That's an infinite region. That's an unbounded region. This region over here is unbounded, this is unbounded, that's unbounded, that's unbounded, that's unbounded. The only thing bounded is that little triangle right there. So that defines our region of integration. That's our region R. So, let me shade it in since it's important and all of that. Okay. Now, what we're prompted for is to evaluate the integral using the order dx dy, and then conversely, use the order dy dx. And then apparently do nothing with all this space up here, because that's a shameful waste of space on my behalf. So, let's do that. Oops, already screwing it up. So I'll use this space up above to define our limits, okay, for the 2 different intervals we want to set up. And they both should evaluate to the same number. They have to, okay? So if I commit to doing dx dy first, okay, when x goes into this region, when I'm going in the x direction, my first order of integration is x, so I want to go horizontally from left to right. So when I enter into this region, what's the first x value that I hit?
X equals 0.
You hit the y-axis, which comes from the equation x equals 0. And if you need to label that, go ahead. I've labeled the other 2. For some dumb reason, I didn't do the third. But that's at the boundary x equals 0. When you go all the way through the region, no matter where you draw that horizontal ray, okay, you're always going to exit at what x boundary?
X equals Y.
X equals y, okay? Because originally that was described as y equals x. That's a symmetric equation. It also says x equals y. So going from left to right, x enters at x equals 0 as the lower limit, and x exits at x equals y, my upper limit, okay? And then, what would your constant limits for y be based on this? Yeah. I've done the x direction. What I usually do with Calc3 is when you're doing the double integrals limits, your first order of integration needs to be drawn through a 2-dimensional region. So you preserve the whole 2-dimensional aspect of this shape as you're going from x equals 0 to x equals y, and then you write those limits down. As soon as you've done that first order of integration, you got those limits down pat, that's why I flatten it 1 dimension less to the y-axis, because this would flatten to the y interval 0 to 1 as y's limits. Okay? Because technically you're going 1 dimension less after you've done that order of integration. So y goes from 0 to 1 as its limits. Yes, sir?
With having it just like that, wouldn't you just be able to tell that as y because it gives you a line at the top part as topping out at 1?
Mm-hmm. I mean, you don't have to do the whole, trash compactor flattening thing, but, I just like bringing up Star Wars anytime I can in class. But yeah, that tells you. And as long as you remember when you're doing these outer limits right here, the outer integrals limits, you got to consider this a 1-dimensional space. you've done the x direction through 2 dimensions, and then technically you go 1 dimension less for the remaining variable's dimension. And that's why I kind of flattened it out so that I really turned this 2D triangle into a 1D line segment that represents the interval 0 to 1 for y. In triple integrals, you're going to do something analogous. You'll have 3 orders of integration. You'll go through in the z direction from the bottom of the surface to the top of the surface, and then you'll flatten it from 3D to 2D. Then you'll probably do the x direction from one x boundary to the other like this, and then you'll flatten it to 1D to get the y limits. So anytime you have multiple orders of integration, your first order is always going to go through the full domain in its intended dimension. 2D for double integrals, 3D for triple integrals, kind of thinking ahead. And then always, I guess, reduce the dimension by 1 every time you switch to the next variable's order of integration. You see what I mean? Mm-hmm. So if you don't like the whole flattening thing, you don't have to make that sound every time you do it. I just, it's just me turning it into a 1-dimensional line segment. So that would become this integral. Double integral. 0 to 1 is my outer one for y. 0 to y is my inner limits for x. And my integrand is x squared plus y squared. And we've committed to dx, dy order. Okay? You set up the other one. Already done it? Only one tiny difference. What'd you get? Oh, you went ahead and did them both? Because if you go in the y direction, the first you're not hitting 1 equals 0 first. Oh, that's x.
Yeah.
Okay, yeah. So beware. Both of these should evaluate as the same, but your outer limits will look exactly the same. I'm going to give you that hint. Your inner limits will look different. Well, because here they should have y's in them when you're doing dx first. Conversely, if you're doing dy first, you should have only x's here. Curious? Confident? Okay, that's good. Much better to be well, no, curious is good. Confident's good too. Need an assist? Okay, you getting it? Just set it up. You don't have to evaluate it. We'll choose one of these to evaluate it. Which one seems to look easier? Isaac, can I pick on you?
Yeah.
Okay. What'd you get for your y limits on the second situation?
0 to x.
How many got 0 to x for your first limits on y? All right, let's double check it. Anybody get something different?
X to 1.
I got x to 1.
X to 1, yeah. Start with a full, fresh copy of the 2-dimensional domain. If I go in the y direction first, okay, what's the first boundary of the shaded bounded region that y actually hits?
Y equals x.
Y equals x. Y equals 0 is a corner boundary down here. But remember, you've got to consider this a full 2-dimensional object. So that's why you need to possibly consider multiple rays that go in the y direction. No matter which way I go, I mean, hopefully that's not me looking silly. Hopefully you see what I'm doing there. Whenever I enter into this, that's always going to enter at y equals x. And then when you go through the 2D space, you're always going to exit at y equals 1. So your limits for y should enter at y equals x and exit at y equals 1. So be careful about that. The only time y equals 0 being on the bottom is if this region came into contiguous contact with the x-axis. Yeah. So, I mean, if you need to do this, I mean, I've done this before. I mean, just go ahead and draw some little rays to help you see what your entrance and exits are. In the y direction, you're gonna hit that first and hit that last. So that lets you know that, my entrance should be y equals x, my exit should be y equals 1. Versus over here, we do the x direction first. No matter what horizontal ray you draw, you're gonna always enter at x equals 0 and exit at x equals y. So then, with that dimension done for y, what does that default your x dimension to? I think I've already told you this stuff.
0.
Yeah, if you flatten this triangle to the x-axis, you're going to have a smudge that begins at x equals 0, and then this tip here smudges down to x equals 1. So the one-dimensional domain for the outer integral would be the x interval from 0 to 1. And look like this for your potential integration pleasure. Now, if you had your choice, which one seems to look easier to do? I mean, your antiderivative is going to be, kind of symmetric because you're integrating x squared first here versus integrating y squared first there, and the other's a constant. But you're choosing the one on the left. Why?
0. I subtracted.
As many zero limits as you can possibly get on integration is always a handy thing. Both of these lower limits are 0. I'm anticipating polynomial antiderivatives. Bless you. Polynomials work well when you plug in that lower limit at the end of the fundamental theorem because it wipes everything out. So that's why I say this one trumps this one in terms of just more zeros to plug in. So if we do complete this volume problem, and I want to, I'm going to integrate x first, and hopefully I've left myself enough room here. When I integrate this with respect to x, I get 1/3 x to the third plus x y squared. Remember that y squared is a constant. You're plugging in y for all the x's. Can y'all see my writing? I feel like I'm writing really small. Good thing I can zoom in. So when I plug in the upper limit y, that gives me 1/3 y to the third plus x times, plus y times y squared, another y to the third, and then minus 0. So both of these should be y to the third terms when you plug in your y there, right? And so that should give you 4/3 y cubed. And then I want to take that and do my y integration. So again, that's just sort of makeshifting. This is what I'm integrating here. 4/3 y to the third should actually become 1/3 y to the fourth, because your antiderivative rule will cancel that 4 out. And 1's a handy limit to plug in too, because on polynomials, 1 just gives you all the coefficients. 0 is even better because it wipes everything out. So whatever this three-dimensional solid looks like, that has this triangle as its base and has this paraboloid as the top of its surface, has a volume of 1/3. I can actually draw that one. The paraboloid is pretty easy to draw. Just to show you a picture of what this thing looks like. Down here in the xy plane, oops, hello, that's not possible. You've got y equals x, y equals 1, x equals 0. So this is sort of a skewed version of that triangle. The paraboloid up above it is basically just that big bowl. But if you're only looking at the snippet that's lying above this, you see a parabola cross-section here for that part of the solid. You'd see a diagonal parabola cross-section coming up here for that part of the solid. And actually, that's a little misleading. It should go higher in this piece. And then you kind of see another little sliver of parabola right there. So we're looking, kind of through this as though it's like made of clear glass or something. It has that triangular base, and it has that sort of convex paraboloid part right there. But then as soon as you go from the triangular base projected upward to the paraboloid, that's the only part you see. See, if the full paraboloid was here, you see its bowl shape